Hello, we are here for our calculus project. In our project we will introduce you to the very effective mode of generating electricity, that is by using the piezoelectric cells. Let's dive into the introduction of piezoelectricity. The piezoelectric effects. Piezoelectricity is the ability of some materials, notably crystals and certain ceramics, to generate an electric charge in response to applied mechanical stress. If the material is not short-circuited, the applied charge induces a voltage across the material. Also, this effect is reversible. Motivation, application. On the premises, campuses of big commercial business parks or colleges, we usually notice the hustle-bustle of a large number of people. Another thing that comes to our notice is the gigantic amounts of power that are consumed by these premises on a monthly basis. Piezoelectricity is the ability of some materials, basically crystals and certain ceramics, to generate an electric charge in response to applied mechanical stress. Based on the aforementioned observations, we could utilize the pressure exerted by the stampeding masses in these places to apply stress or strain to the piezoelectric substance, generating some power that could help power the premises. If there is a direct way of using piezoelectric cells, then they can also be used in a converse way. This functionality of a piezoelectric cell is called reversibility. Here are the types of piezoelectric effect. The first type is the direct piezoelectric effect, the production of electricity when stress is applied. The second type is the converse piezoelectric effect, the production of stress and/or strain when an electric field is applied. Example: lead zirconate titanate crystals will exhibit a maximum shape change of about 0.1% of the original dimension. Simple molecular model of piezoelectric effect. Before we apply any external stress, the centers of positive and negative charges coincide as on vectorially adding dipoles. The net dipole moment turns out to be a zero vector. After exerting a bit of pressure on the material, the internal structure is deformed, which eventually causes the negative and positive center separation of the molecules, and very little dipoles are generated as a result. How it works: the facing poles inside the given material mutually cancel each other, and a linked charge appears to be distributed on the material's surface, hence the material is polarized. The polarization of the material eventually generates an electric field, and then it can be used to transform the mechanical energy produced due to the deformation of the material into electrical energy. Image shows us the actual construct of a unit that uses piezoelectric discs that are to be placed underneath ground. The first diagram, labeled A, shows the outer structure, whereas the image B gives us an insight of piezoelectric discs used with diodes. Formulate and solve the mathematics. The quantities used in the equations contains three types: scalar, vector, tensor. Equations of motion, elastodynamics. Explanation. In the above-mentioned equation, del into T is the divergence of tensor field T. It basically measures the rate of change of field T at the point of examination. F is force vector field. From the POV of mechanics, fluid dynamics, F could possibly represent an external force applied to the system. U represents velocity vector as a function of time, and we have differentiated it twice to take acceleration of fluid into consideration for constitution of equation. The equation is a form of Navier-Stokes equations used to describe motion of viscous fluid substances. Gauss law, electrostatics. Explanation. Once again, in this equation, del into D represents divergence of electric displacement vector D. We know that this D is related to electric field E and polarization of the medium. It basically measures the rate of change of field D at the point of examination. In this equation, as Q that shows volume charge density, which is basically electric charge per unit volume. This equation is form of Gauss law for electric fields in material. Thus this equation relates divergence of electric displacement fields with volume charge density of the material. This equation is occasionally used in analysis of dielectric substances. Kinematic relations. Explanation. Then above-mentioned equation Sij represents element of strain tensor. Strain measures how much a body deforms when under stress. Uji shows partial derivative of Uiwrt the coordinate xj. It is like a displacement gradient. Uji similarly shows partial derivative of displacement xi with respect to xi. 1 by 2 is multiplied to ensure symmetricity of strain tensor. This equation is a way of showing strain tensor in terms of symmetric part of gradient of displacements. Maxwell's law. Explanation. This equation relates electric field E to gradient of electric potential phi. EI is with component of electric field. Minus del is the negative gradient operator, and phi is electric potential. Here we have taken gradient of a scalar field like electric potential. This is a vector, and this points in the direction of the steepest increase of the field. Minus sign hints that electric field points in the direction of steepest decrease of potential. Usually, piezoelectric materials exhibit coupling between mechanical and electrical properties. This equation demonstrates it very well. This equation relates electric field to negative of gradient vector of electric potential. Constitutive equations with piezoelectric coupling. Explanation. This equation is a constitutive equation involving piezoelectric coupling. T is stress tensor, which is explanation of forces within a material. C is elastic stiffness tensor, which describes the deformations in response to applied stress. S strain tensor. E is a matrix known as piezoelectric coupling matrix, which describes an interaction between electric field and mechanical deformation in a piezoelectric material. E is vector of electric field. This equation demonstrates the phenomenon of how stress in a material is influenced by its elastic properties and response to applied electric field. Piezoelectric materials show a coupling between mechanical and electrical behaviors. Explanation. D represents the electric displacement vector, which is amount of induced electric polarization in response to mechanical deformation. E is piezoelectric coefficients. This quantifies degree of coupling between stress and electric polarization. S is stress applied to piezoelectric material. Epsilon could represent permittivity of material. E is electric field vector. This equation relates electric displacement and stress and electric field E in piezoelectric material. Boundary conditions, uncoupled, Ui cap, phi cap at the specified mechanical displacements, m, and electric potential, v, and Fi cap, q cap at the specified surface forces, n per square meter, and surface charge, c per square meter. Ni represents the outward unit normal vector components. Final set of partial differential equations. 1. Piezoelectric equations in primary dependent variables. Explanation. In the above equation, ρ denotes the density of the fluid. U denotes velocity vector of fluid. U is the second derivative of velocity vector, which is expressed as a function of time. Del represents spatial gradient. C denotes stress tensor. Del into U is gradient of velocity vector. E denotes electric field vector. Del into phi denotes gradient of electric potential. F is external force acting on fluid. This equation incorporates an application of Newton's second law of motion. Explanation. This equation is a partial differential equation of electric field in a medium. Del represents the spatial gradient. E is electric field vector. Epsilon is dielectric tensor or permittivity tensor. Del into phi is gradient of electric potential. Q is charge density. Here the first term represents divergence of product of electric field and velocity gradient. It is a concise description of how electric field responds to changes in fluid velocity. Second term is known as the dielectric term, gives us negative divergence of product of dielectric tensor and electric potential gradient. How a medium would react to an electric field, influencing distribution of electric potential, is shown by this term. Minus Q term is a representative of a source and sink of charge density in medium. 4 forms of constitutive relations. 1. Stress-charge form. Explanation. T represents stress tensor and D denotes electric displacement. C is elastic stiffness tensor when electric field becomes constant. Epsilon denotes the piezo minus electric coupling tensor equation. After the above, one relates electric displacement to stress and electric field. 2. Stress voltage form. Explanation. T represents stress tensor and D denotes electric displacement. C is elastic stiffness tensor when electric displacement becomes constant. Q denotes piezo minus electricity coefficient. This equation relates electric field with stress and electric displacement. 3. Strain charge form. Explanation. S denotes strain tensor. D represents electric displacement. S denotes the elastic compliance tensor when electric field becomes constant. D represents piezo-electric strain coefficient. The second equation shows electric displacement as a function of electric field and strain. 4. Strain voltage form. Explanation. S is the strain tensor. S denotes elastic compliance tensor when the electric displacement becomes constant. G denotes the piezo-electric voltage coefficient. The second equation relates electric field with strain and electric displacement. Some uses of piezoelectricity. 1. Lighter. Piezo ignition systems can be operated by either a lever, push button, or built into the control knob. An electric spark is usually generated once per turn of the knob or press of the button. 2. On road, we can generate energy by putting piezoelectric sensors within the road. Because of the transportation of heavy vehicles, we can gain much higher energy through this piezoelectric cell. 3. In shoes, this simple structure of piezoelectric cells implemented in our shoe can be used to charge our mobile phones and generate some electricity just by walking or running in regular basis. Thank you for watching this video. Hope you understood the concept of piezoelectricity.